Today we are here for the last lecture in the initial lecture series here on the density-based method presented by Professor Ole Sigmund. Today the sort of main focus will be multiscale within density-based topology optimization methods. And then I can announce that we will have equally 3 lectures on the level set methods or the level set method in May. So these will be presented by Professor Gregoire and with assistance from Charles Capocni. Sorry for my butchering of the names. So these will be in relatively rapid succession in May, so over the course of 3 weeks, because that's what we could make work. But similarly to these 3 lectures on density-based methods, we will have sort of a general overview and then some more specific lectures following up on that. And so the links to sign up for these will be sent out on the mailing list very soon, and I will also post them on our website. And you can always also follow me on LinkedIn and however else we try to get this out. So this is brand new information and you can look forward to that. So now let me find the stop sharing button and then we can pass over to Ole. Again, Ole needs no introduction, but Ole is a pioneer from within topology optimization in general and in particular density-based methods, and will be concluding his lecture series here today. Okay, go ahead, Ole.
Okay, thank you so much, Joe, and thank you again for inviting me to do this. It's a great pleasure also for myself to try to sort of sum up on many things that I've been involved in and my insights in the field. And as you all know, the topic was 3 tutorials on the density method. And you could ask, hey, how does it work? Density method, and then the 3rd tutorial is on multiscale. How does that connect? Well, surely they are very tightly connected. Partly people are doing what we would call density methods on several different scales and combining them. So that would be one thing. Also, I think you cannot really do simple density-based topology optimization without knowing the background from multiscale and the theory of composites and stuff like that. And finally, I would also say, as I've alluded to in several of my earlier slides, the distinction between the different methods in our field are really not as big as it sometimes looks like when you read the literature. Density methods, level set, topological derivatives, multiscale, and all this business, I think it's sort of one and the same thing, but in different flavors. But to motivate further, let me start by just repeating a couple of slides from the previous tutorials, and also remind that people in YouTube, if you watch this tutorial, then it's a really good idea to start with tutorial 1 and 2 that can be found on the top webinar, and then go on to this one. But otherwise, I think you can also follow this one alone. So to go back, I show these pictures here of sort of the history behind topology optimization. So how Cheng and Ole have found this mesh dependency, and how applied mathematicians came up with the optimal microstructures, so-called rank materials. And then these ideas were adopted by Bensu and Kikuchi and led to the original homogenization approach to topology optimization. So at that point, partly it was difficult to realize these structures, and partly the method was quite complex, at least for some in some ways. And for those various reasons, then everybody switched to the density methods that were later called SIMP methods, and we had the big developments in that field. But I will actually show how we get back to the original ideas in a second. Then, so that was the first tutorial, and I went through how we defined the density approach. I said that for certain values of P, typically larger than 3, then we actually have physically realizable microstructures. And I set up this sort of standard density-based topology optimization problem as seen here. Then in the second tutorial, I went into filtering techniques and regularization and stuff. And at the very end, I spoke about these advanced filtering concepts, which we call local volume constraints. So essentially, we added an extra constraint, which constrains the p-norm of the difference between a filtered density value within a certain radius and a prescribed density value, rho c. And so by that you have a local volume constraint, which means that you are sort of enforcing a microstructure. Because under every little circle, as indicated with the red circle here, there can only be so much material. And so in that way, solid material is not possible and you enforce the microstructure. And so this gives beautiful structures and it's really fun to play with, but you could say it's sort of crossing the river for water, because why do you use an extremely fine resolution density approach to mimic something multiscale? And so here we are sort of bridging the gap back to multiscale. And if we look at some of these structures generated by the local volume constraint, then we will look, so there's in 2D and in 3D, and if we take a magnifying glass, we will actually see in the 2D case, if we just consider a single load, and we take a magnifying glass, then we will see that the microstructure is sort of a rectangular microstructure where the material is oriented along the principal stress directions. If you look at the multi-load case, then you also have these square regions or rectangular regions, but you actually also see regions where there are like triangles. And also in 3 dimensions, and you look at with a magnifying glass again, you will see for single load case that there are these orthogonal layers of plate-like structures. And so this actually indicates optimal microstructures. So you could say for single load case in 2D, you have orthogonal layers, 2 layers of microstructure. For multiple load cases, you see 3 layers. If I had done a 3D case with multiple loading cases, I would see up to 6 layers, it turns out. And this is not a surprise. This is actually the insights by applied mathematicians that led to the original topology optimization approach. So they didn't see these local volume constraint structures, but they looked at optimal microstructures and they compared to theoretical bounds. And with that, they actually came up with this beautiful mathematical theory of rank in laminates. And as I already said, they already back then said, if you have a single load case, then the optimal, the theoretical optimum, you cannot do it better. The optimum structure consists of a layering at 2 different length scales, perpendicularly oriented in the direction of the principal stresses, and with lamination thicknesses corresponding to the principal stress absolute values. And so that's for the single load case. If you have more load cases, then they could also prove that the optimal structure consists of 3 layers at different length scales. Not 4 or 5 if you have 4 or 5 load cases. 3 layers is enough for an arbitrary number of load cases. And so that led to this rank 3 material. And likewise, in 3D, if you have a single load case problem, then it's 3 orthogonal layers at different length scales. And no matter how many load cases you have, you only need at most 6 layers. And so 6 layers can also produce an isotropic microstructure. So you could say these microstructures or rank n laminates, they are mathematical constructs. They don't have stress concentrations, and that's sort of why they are so optimal. But it turns out, and we've seen that also already in the beginning works by Benzu and Kikuchi, that actually making an interpretation of these multi-rank or multi-length scale laminates to a single length scale doesn't deteriorate the stiffness very much. So typically we see that by making a simple 1 length scale structure and maybe adapting the corners a little bit, well, then we deteriorate the stiffness by maybe 5 to 10%. But in reality, or mostly, we are actually still recovering something very close to optimal microstructures. One important observation here is that specifically in 3D, the optimal microstructure consists of plates. So it's going to be a closed-walled microstructure, so a plate-like lattice structure. And often you see people using truss-like lattice structures and claiming these are also lightweighting. But it's very important to note here that trusses are actually not good for stiffness, because trusses can only take load up in one direction. The plate-like structures can share load between different directions in the same material. And so therefore, truss-like structures are up to a factor of 3 less stiff than the plate-like structure. So that's very important, and I think it causes a lot of confusion when people are saying, I do topology optimization with truss-like structures for stiffness. That doesn't make sense. The optimizer should not select the microstructure, it should select the solid material and not the truss if the goal is just to optimize stiffness. So I'll come back to that, but that's a common misunderstanding. But so these are the optimal microstructures. So we actually know the theoretical optimal microstructures in this case, and this is exactly the fact that Benji and Kikuchi used in their old works. And so they computed for these ranked materials. So that was actually in Martin's paper, this one. He could compute the theoretical effective properties of these ranked materials in closed form solutions. So very beautiful mathematics and stuff. And then they devised this algorithm where you have 3 variables, the optimal orientation, that you're orienting along the principal stress direction, and then those 2 lamination parameters, the thicknesses, and then they got these pictures. The unfortunate thing back then was that, well, they knew the locally optimal microstructures, but they didn't know how to sort of transfer that to something physically realizable. And so this is sort of part of the reason why we switched to density methods. But meanwhile, we have figured out how to do it. And just before getting to that, well, that all builds actually on the old homogenization approach. And so I'll just shortly say, so this is the optimization problem we have now. So instead of 1 density variable per element, we have 1 rotation variable per element, theta, and then those 2 lamination parameters. And the effective properties are given by this closed form solution where R are rotation matrices. So it actually calls again for a very efficient code. And in fact, in the review paper that we wrote with Junwoo and Jerome Grön, there's actually an attached MATLAB code that produces these optimal homogenized structures. And so the result of this code is the one you see here. If you enlarge, then you see that every element has a direction vector, or 2 directions actually, red and blue, and corresponding to the 2 lamination directions. And then the grayness is the density, and the size of those 2 vectors there, they correspond to the 2 lamination parameters. And so interestingly, since the rank n material, or the rank 2 material in this case, these are single load case problems, is the theoretical optimal structure, then if you use those for your optimization, you get a lower bound on the achievable compliance. So I'm actually suggesting for everybody working with stiffness-based optimization, multiscale or single scale, you should actually run this code, and that provides you with a theoretical minimum compliance or maximum stiffness, and you can use that to benchmark your results with whatever method you are using. So that's one recommendation here. The problem is, however, still, how do we realize? Well, okay, sorry. So this was first for the rank 2 materials. As I said, if we switch to a single length scale and essentially have a rectangular hole and vary the thicknesses of these holes there, well, then we get similar results. They are slightly less stiff because it's slightly less optimal than the rank 2 materials, but essentially the thing is the same. It cannot be put in as nice a compact MATLAB code as the one for rank 2 materials, because you need to have a database where you compute the effective properties of the rectangular holes for different parameters, and then you should interpolate for that, from that. But that's still a doable thing. It's not a big thing, but I don't think there is a MATLAB code available for it, but I think it should be fairly simple to do it. So anyway, we know how to do homogenization, and it can actually be done quite compactly. The problem is still, how do we realize these structures once we know what the optimal hole distribution is? How do we actually physically realize these structures? And so that was the big headache. And you could sort of take the naive approach and just say, okay, we optimized with some coarse elements, and then in every element we just draw this rectangular microstructure and put it together, and then you would get a picture looking like this. So you sort of do see some effects here, but obviously having these weird microstructures that meet would create a lot of bending, and it's not the real microstructure, right? So this naive way cannot solve the problem. And so this is sort of where the original homogenization approach was stuck. We don't really know how to realize that. So while not having that solution, people started suggesting to do what I would call multi-level or two-scale density approaches. And so there are many works on that. I'm not mentioning names here, because no names mentioned, no names forgotten, but there are so many beautiful and very interesting works on this. And so the idea is that you are sort of both looking at the macro scale and then on the micro scale. And at the micro scale, you homogenize the properties, so you have a periodic microstructure, and you actually do a density-based topology optimization inside each cell, and then you those properties map back into the macrostructure. And so essentially you are solving a localized density topology optimization problem in each of the global elements. And then there's some interrelation here, and you control the overall volume is controlled by the macrostructure and then propagated down into the microstructure. And these give a lot of insights. So here you would see that the microstructure changes according to the local stress and strain states. But there is two problems here, actually. So one thing is you're sort of constraining yourself to microstructures that can be built into a square box. And they have to be periodic, so they have some constraints on that. The other thing is that the homogenization doesn't consider boundary conditions. So there's nothing that between two cells here says that they have to be connected. And so you're sort of fighting two things. You're getting non-optimal local structures because you're restricted to something that fits into a square cell, and you have to somehow make these structures connected. And again, in the review paper, we are discussing many different methods. So others, they then introduce suboptimal but simply parameterized structures where there's a guarantee that they will always be connected. But as you will see later, as soon as you start having suboptimal structures, then microstructure is not really needed anymore. So that's an interesting thing. So you're sort of destroying the purpose of multiscale stiffness design by not using optimal microstructures. And I'll come back to that in a little while here. To circumvent or to avoid this connectivity or compatibility thing, there has been many works and still many coming out on connecting two neighboring microstructures. So in this case, I stole from some work out there. We see if we don't do anything, then the microstructures are hardly connected, but then you can put some constraints saying that neighboring microstructures have to be connected. But that's actually a very strong constraint, because if two neighboring microstructures have to be connected, it actually also means that a microstructure at the left end of the structure has to be connectable to the right edge of the structure. So it's a very strong constraint. And again, that means that the use or the motivation for microstructure is actually jeopardized. And what you will see is that many papers that do these multiscale approaches, they actually enforce microstructure artificially, a bit like in the local volume constraint. So they're saying they're not allowing the density locally to vary freely. They say it can only go between 30 and 70%. If they don't put that constraint on it, the optimizer would actually go to completely solid and void, and the microstructure would not be needed. So that's an interesting observation, and I think it's important when you do such works that you realize that these are not stiffness optimal. And I would go as far as claiming that stiffness optimal multiscale structures cannot be based on simple fixed cell based microstructures. So I'm pretty much saying here that this is not the right way to go. It's debatable, but I will come with more arguments later on. So now what do we do then? Well, for that, we have invented the so-called de-homogenization method. So we have the homogenization result, we want to de-homogenize it to find the actual structure that will realize these properties. And I will go through 3 approaches here that I call auxiliary fields approach, the AI or deep learning approach, or the phasors approach. And let me just take the first one first. And actually, I should say this is inspired by beautiful work by Pantz and Trebelsi. They did it back in 2008. Nobody understood it. Nobody appreciated it for many years. I think until Jerome Grön and myself sort of rediscovered it and brushed it up and made it more accessible. And then this field has seen a huge revival. And also Grégoire Allaire and co-workers have done multiple interesting works. So the idea is we start with this coarse scale homogenization-based solution that we have the MATLAB code to do, that gives us these local directions and stuff. And so essentially for every element in the structure, we know 2 unit vectors that give the normals to the layers. And we have the parameters A1 and A2, which are the lamination thicknesses. And the question is, how do we extract the structure from that? The idea of the auxiliary fields approach is the following. So we introduce 2 auxiliary fields. They are scalar fields. They exist again in a finite element setting. So it's a cheaper finite element problem to solve because it's only scalar compared to the vectorial one for the elasticity. Then the solution we are seeking is the least squares minimum of this objective function, which says that we want the gradient everywhere in these fields to be equal to the normal of the layer, the E1 component coming from the homogenization here. And so this objective here minimizes that. So it says essentially that the gradient of the phi field is equal to E1 distributed over the domain, and the gradient of the phi 2 field is equal to E2. And this, you cannot solve this exactly, but you can get it sort of in an approximate fashion. And we put an additional constraint on it to say that we emphasize that the 2 fields should be orthogonal to each other, rather than we can say the norm of the gradient doesn't exactly need to be equal to 1. We relax on that, but we insist that the 2 fields gradients should be perpendicular to each other. So what do we do with these 2 fields? Well, those are the clues. So let's take them on to the next slide here. So these are the 2 fields that have this special property. Then we do something very simple. We just take the cosine to these, the gradient of the field times the local coordinate. And we multiply this with what we could call a periodicity factor. And that gives us these zebra stripes. You can already see it here. You have the contours here. And when you take the cosine to that, you sort of get stripes according to this periodicity. And so we have these 2 fields, and you already see here they are sort of perpendicular to each other. They are still missing the information of the layer thicknesses. So the next operation is to say, now we threshold these fields at a value that makes them satisfy the layer thicknesses or correspond to the layer thicknesses. So that's done with this Heaviside function here. And the thresholding is then based on another cosine function that depends on these lamination parameters. And at the end, then we take those 2 fields, put them on top of each other, and select the maximum value of it. And then we get such a beautiful structure here for almost free, since it's just based on one topology or homogenization-based topology optimization in a coarse grid. And so what we see here, there's some post-processing. The original method produces a bit of noise. There are some post-processing steps, but they are fairly inexpensive. And what we see is that we have speed-up factors in the hundreds or even up to 10,000s in the best of cases here. So this is essentially the de-homogenization method based on auxiliary fields. And how good or how well is it performing? Well, you could take one of these classical design problems. This is the 5x8 cantilever beam. And we get for the homogenization-based solution, so using the MATLAB code, we get a compliance of 71 in this case. Then we perform, perform the de-homogenization. It takes us like 3 minutes or something like that. and we project it to a very fine grid and compute the compliance, and it's 72.6, so it's like 1% higher than this one here. So we lose a little bit, but it's actually surprisingly little, so it's actually very efficient. And usually we stay at most 5% errors, even for the more difficult problems. Then you could ask, how does it perform to a standard density-based topology optimization? And here we did it for the same ultrafine mesh in 2D. That took forever. And you could say, actually, in this case, the compliance is worse. So we actually managed to beat the heavy density-based approach with this de-homogenization approach. Sometimes the answer is opposite, as the next slide will say, but the main thing is we are in the right ballpark and we can save a lot of time. This was for the single load case. Now to the multi-load case problem, that gets actually quite a bit more difficult. And so recall in the beginning I said that we know for the multi-load case problem that the optimal composite is always has 3 layers or up to 3 layers. And so in this case, it's a bit more difficult. There's another difficulty that the directions are non-unique. So it's difficult to trace which directional field belongs to each other. And therefore, it's also somewhat difficult to solve these auxiliary problems. So that's one of the headaches, and it's not really well resolved for the multiscale problem yet, but I can show what we did so far. So again, we are doing a SIMP-based reference design. Again, it took for ages. Of course, you could run with a coarser discretization, but sort of for the fairness of discretization, I show this case here. Then we do the homogenization-based topology optimization with 3 layers and do this ordering and stuff and perform the de-homogenization. And in this case, you see that it's like 2% worse in compliance, but again, the timing is so much better. So you really gain a lot by doing this de-homogenization. Right, and of course this can also be done in 3D. We have multiple beautiful works on that. There are different issues, again, also with singular stress, singular points where you have to do special things, but overall you can do very beautiful structures here. This is the classical bracket example. I remove the surface and you see how, depending on how many layers we adapt, we get these beautiful structures that locally adapt to the principal stress directions. So this was one approach. It works very nicely, but there is the thing, you have to solve these auxiliary fields. And also you could say, hey, isn't this something where we could maybe use AI or some deep learning? Because it's really, we have a stress field and we have directions, and we have to translate it into some kind of periodic structures. So that seems like a fairly trivial task that can be trained. So we asked ourselves that question together with our colleagues from the computer graphics department, Andreas Berntsen and Martin Ellinggaard. And the idea here we said was, well, a bad thing about many AI-based topology optimization methods is that it's very expensive to generate the training data. Because every training data needs a topology optimization, and that sort of kills it. It becomes extremely expensive to train. Here we could say, hey, we don't need any topology optimized training data. We just need vector fields or orientation fields. So we generated a lot of random orientation fields, put them into a Gaussian encoding, and fed them into a convolutional neural network. And then we trained it on pictures that we wanted to, how we wanted to have them look like, with periodic patterns and stuff like that. And that worked actually very well. So we came up with a method that works for arbitrary homogenization results. So now we go to an actual physical orientation field. We let it go through the neural network backwards, or in the trained network. Then we get out some intermediate field that needs some post-processing. So there are some post-processing to connect the lines and do different things, but that could sort of be done in an image processing fashion. But at the end of the day, we had a very efficient algorithm And the nice thing was that we could apply it. So if we fed it a finer input structure, so a finer homogenization-based input structure, we would also get a finer output structure, and it was very efficient. So here, this was still in a, I believe, in a Python script, 2 seconds to dehomogenize here and 20 for this one. So we thought, wow, this is the first time we have actually found that you can use AI to really save time in topology optimization. But then we had, well, partly our colleague Berensen, but also a clever student, Rebecca Wallstedt. They sat down and worked on what we call phasors, a phasor approach. So this is the third approach. And so phasors is something that comes from the image processing or computer graphics environment. They are also called Gabor kernels. And it's a long story here, but to try to make it short, it essentially is a product of a Gaussian function with a compact basis and a periodic field. And that gives you these small sort of wave packets. And with those, we introduce one of these wave packets in each of the elements that we used in the homogenization approach. We orient it according to the local orientation. And then we do some local operations like adapting the local phase of these phasors to get the best possible fit. And when we then get the result, we get such periodic patterns that look like something of what we want for the dehomogenization. They are still not connected. So Rebecca did various squeezing and quenching operations and all kinds of stuff. So it's essentially post-processing. And then she was able to produce these connected structures. And this is not simple, but we published this MATLAB code 2 years ago, which is now called an 808-line Phasor-based dehomogenization approach. But essentially that does the job for you, and I invite you to play with it. It's actually quite efficient. So we get lots of beautiful structures out of that. Conclusions are similar to before. We just lose a few percent during the dehomogenization. So these are extremely efficient approaches. And it's actually so efficient that we really would love to make it interactive. We have unfortunately not managed to do it yet. But this is actually just running the MATLAB code, slightly sped up. Where we are doing the homogenization, we are doing 20 steps homogenization, then we take one dehomogenization step, and you sort of see how the multiscale approach almost gets a real time here. So our dream is still at some point to make a multiscale top-up app. We haven't gotten to that, and I guess I can also say here, if somebody is interested in doing it, we would be really happy to collaborate on that. But I think this shows how efficient this actually is. So this was for stiffness optimization. The dehomogenization works also for other cases. So together with Shelley Zhang and her group, we looked at cloaking. Again, here that there has been people who do the 2-scale topology optimization approach. So essentially doing every element in is one microstructure, and they optimize density-based topology optimization in every microstructure. They have these connectivity problems, but it's not as big a problem in cloaking cases, because there they are not looking for the optimal, the extreme structures, but it's more an identification problem of finding a microstructure with certain properties. So it sort of works okay, but it's extremely inefficient, right? Because you have to solve one topology optimization problem for every cell in this case. We showed with Shelley that we can actually use the dehomogenization approach as presented with these auxiliary intermediate fields. In this case, there are 3 of them. And we get these beautiful and very intuitive structures. So that's one application. And another multiphysics or alternative physics application is actually done by our chairman, Joe Alexanderson, and co-workers, where they used dehomogenization code to produce thermo-fluidic structures, and again, with great success. So I think it's a really powerful tool that can solve a lot of problems extremely efficiently when you have something multiscale. Okay, so now we have this tool. Let me go back a little bit and talk about the motivation for microstructure, because I've sort of been saying that if you don't use optimal anisotropic microstructure, then there's no need for microstructure. So what am I saying here? So let me just remind you of the slide I had in the first tutorial. And so this was the interpolation function that we use, the SIMP approach, where we have the Young's modulus as function of the density. And I showed here that for SIMP power p equal to 3, that's the blue line, then we stay below the theoretical achievable material properties given by the Hessian-Strickman bound. And we have this effect that we penalize intermediate densities, and hence the optimizer doesn't want that in the optimized solution. So depending on which power we get more and more black and white structures. And then I asked the question, well, what if we use the optimal isotropic microstructure, which turns out to be this triangular microstructure, as the interpolation? And I tried that, and I also got black and white structures. So that's this interesting fact that people are overseeing, I think, is that even an optimal isotropic microstructure is not good if your goal is to optimize stiffness or minimize compliance. So that's a very important insight. And so you could sort of say, so why have microstructures at all? And so the conclusion here is that optimal isotropic microstructure is not efficient for compliance minimization. So and just so one extra slide here, just to sort of say, so how come anisotropic microstructures are optimal or are good? Well, you see it again here. This is the same picture, but now here I'm plotting with yellow. These are the properties that you achieve by having either rank 1 material gives you a linear interpolation, and rank 2 material gives you this other interpolation. And we see here that the properties you achieve for a certain density are much higher than the SIMP approaches and the Hessian-Strickman bounds. And that's why it's actually an advantage to use microstructure if it's anisotropic and adapted to the local stresses, but it's not an advantage to use an isotropic microstructure, even if it's the optimal one, when the goal is to optimize stiffness. So then why would be, or isn't there some cases where it's good to use microstructure, even the isotropic one? Well, the clue is you have to look at other things than the compliance. And I think we have been too lazy in the field, always looking at compliance. We should really look at other cases. And so one case we looked at was in the Chinese journal Engineering here, was to say, hey, what if we use this infill approach with the de-homogenisation and generate structures that have the same volume than the SIMP approach, but it has this infill. And what we see here is that the bars become thicker since we have porous infill, so the bars become thicker. This means that the stiffness gets worse. So it means the stiffness of this structure is 30% lower than the SIMP solution. So that's the cost. The stiffness goes down. However, since the bars are thicker, we saw that indirectly we get a higher buckling load. So in fact, the buckling load of this structure is 5 times higher than the SIMP structure. So the conclusion of this paper, and we also checked it both numerically, non-linearly, and with experiments, that the conclusion is if we sacrifice stiffness a little bit, then we can gain a lot in buckling even when using isotropic porous microstructure. And so this motivates the use of isotropic porous microstructure. In fact, the failure of this experiment here, of the beam here, was actually not global buckling. It turned out to be local buckling. So we were sort of lucky in this example, and it was only a postulate that we said, hey, porous isotropic microstructure will increase buckling loads. But we had to prove it, right? Because it's not a given thing. So the next step I will do is actually to introduce buckling as a criterion for multiscale structures. And here I will consider both local and global stability constraints. So let's start with an example here. And again, buckling, I'm not going to go into all the details about how to do buckling optimization. Again, there is a MATLAB code written by Federico Ferrari and his friends here that you can download and play with. But so I will mostly just show you the results and conclusions of this. So to begin with, I'm considering a design domain with an extremely simple case. I just have two loads working in the opposite direction, so I'm compressing essentially a column. And I want to optimize that. And to begin with, as my reference structure, I'm minimizing compliance, and I'm using the Hessian-Strickland bound as interpolation. So in principle, I could get microstructure, but the optimizer doesn't want it, right? Because it's not optimal for stiffness. I put the compliance and the eigenvalue, or the buckling eigenvalue for these as reference. Then I take the Federico's MATLAB code for buckling and optimize using the SIMP approach, so I don't allow microstructure. I allow the compliance to increase with 10%, so decreasing 10% stiffness. And what I see is that I can almost double the eigenvalue. So by making this sort of wider beam here, I can improve the buckling value. Then we could go back to our Hessian-Strickland interpolation and say, what if I now allow optimal isotropic microstructure, so a triangular microstructure in the optimization? And in that case, we actually get microstructure. So not for stiffness, but if we look at the buckling case. And in this case, it seems like it's pretty much constant low density in here, so it's sort of making a grid work of the triangular structure in there. And theoretically, we actually get an even higher buckling value here at the same stiffness between these two structures. The problem is now to check that this is actually correct, we have to do a de-homogenization, right? So in this case, it's very simple because the microstructure is triangular. So it's very simple to do. You can read in this paper by Christopher Christensen. But the problem is if we compute the buckling load for this de-homogenized full-scale analysis, we see suddenly that there's local buckling here, right? So if we don't consider local buckling, then we get a global buckling mode that's high, but in reality, there will be buckling in the local microstructure before the global one, which means that our hypothesis that introducing microstructure helps buckling is only conditionally true. We also have to check that the local buckling is not violated. And so how to do that? That's also a long story, but essentially it's sort of, you could call it an advanced homogenization approach. You take the periodic microstructure, you take out a unit cell, and then you do your buckling analysis in this unit cell. But if you just use the standard periodic boundary conditions as is normal for computing stiffness, then you will not have freedom in your buckling mode. So you will only be able to look at periodic, cell periodic buckling modes. So therefore you actually have to solve this buckling problem for all imaginable periodicities of the buckling load. And this is called Floquet-Bloch wave analysis. So you have boundary conditions that are controlled by a wave vector here. And essentially you have to solve one eigenvalue problem in the cell for every value of this wave vector. And if we do that, so I'm plotting here the colors are the lowest eigenvalue for different values of this wave vector. Then you will see for different wave vectors, you get different periodicities of the microstructure. And the most critical value, that turns out to be very close to 0 here. And due to symmetry, we actually don't need to plot this full picture. We can just look at a band diagram where we are looking at these wave vectors around this triangle here. And it turns out in this case that the most critical value of the buckling value is this one here, not at 0, so not cell periodic, but just after. And that's actually the global shear mode of this microstructure, which is sort of natural. So in this case, it turns out that the buckling mode locally is given by this worst case design. And so this is what we need to do to be able to include microstructural buckling into the multiscale approach. Meanwhile, we could also optimize on the local level, right? So we could actually maximize the minimum eigenvalue. And that's something we did with Christian Thomsen. We did it for different sort of base structures. For the square cell structure, we got this hierarchical structure. And for the triangular one, we got this hierarchical structure. And again, the conclusion is that with small sacrifice in stiffness, you can increase the buckling load tremendously. And in principle, we could now go ahead and say we use these already hierarchical microstructures as a basis for our homogenization approach. This is possible. So this here shows advanced microstructures de-homogenized by both Jerome Grön in his original work and also with the Phasor approach by Rebecca. But these are really not only showcasing what's possible. We actually never got to topology optimized with these optimized local buckling structures. So this is an open problem that I think still is interesting to look at. But meanwhile, we have done topology optimization where we only look at a simple triangular structure. So that one is already pretty good. It has a much higher stability than the square structure, and it's isotropic, so we also don't need to orient locally and stuff like that. The only thing we need to do is to establish the buckling yield surface for such a triangular microstructure. And Christopher, my former student, did this beautifully. So he took the triangular microstructure, added the different loads, computed the buckling loads, did it for different orientations of the microstructure, extracted a yield surface, which is a William Wonke yield surface, and he did it for different volume fractions. And so in that way, we sort of found the most conservative yield surface for triangular microstructures for their buckling stability. And we then used that in the topology optimization in a multiscale approach, where we use the effective stiffness given by the Hessian-Strickman bound, and then this buckling yield surface that we estimated from a very extensive block waved stability analysis. So again, I don't go into details, but all this is explained very beautifully in the papers. And if people have questions, they are very welcome to contact us. So I'm still a few slides from the end, but let me just summarize some results here. So this was a result I showed you before for this simple compressive example. If we just said we allow the microstructure to be whatever it likes with the Hessian-Strickman bound, we got this local buckling. But if we take it into account, so now we have local buckling as a local constraint, a bit like stress constraints, but with a more advanced interpolation function, then we get this structure. And we see now that it doesn't use microstructure everywhere. And when it uses microstructure, it has a higher density than before. And so we lose a little bit in the eigenvalue compared to before. But the exciting thing is what happens when we de-homogenize. And in this case, this shows the de-homogenized first eigenmode. And we actually see that the eigenmode or eigenvalue is higher, even higher than we predicted from the homogenization-based result. So this is a success. With taking this into account, we can actually make use of isotropic microstructure to improve buckling loads. And another example, let me just say, so the first two cases, this is for SIMP-based compliance and buckling. But again, if we include the local buckling as a constraint, then we get this structure. And here we really gain a lot in the eigenvalue. And again, it's interesting to see if we then de-homogenize, then we also have to check, does the de-homogenized solution actually correspond to the homogenized? Otherwise, it's not worthwhile anything. So we tried, and actually in this case, we tried to de-homogenize with different periodicities. So you would sort of expect if you have a very small, fine length scale, then it should perfectly correspond to the homogenization solution. But as you get larger and larger cells, it should deviate more and more from the homogenization solution. But our experience is actually that things are surprisingly robust. And even in the last case where we are really violating the separation of scales, it turns out if we actually do the modeling on the fine scale with the de-homogenized solutions, we again even get better eigenvalues than the homogenized solution. So this sort of shows that we are accurate. And why do we get better? Well, our local buckling constraint was conservatively estimated. So we could do it more precisely and then probably gain even more. The last little point here is now we are taking local buckling into account. But obviously you would also say, hey, there are stress singularities in the corners here. So you should also include the yield stress. And so this was the last work that Christopher did in his PhD. So he, apart from these William Wonke buckling yield surfaces, he also computed the von Mises yield surfaces for different volume fractions. And so we combined that into one yield model. And interestingly, if we look at the blue structure, so that's for a high volume fraction, then we see that the yield surface, the plastic yield surface, is always smaller than the buckling yield surface. So it means that for higher volume fractions, it's only the yield stress constraint that is active, or the plasticity stress constraint. However, if we have a lower volume fraction like the orange one here, then for compressive stresses, it's governed by the buckling yield zone, and for tensile stresses, it's governed by the von Mises stress. So it makes things slightly more complicated. The interpolation laws get more complicated, but still it's sort of following the things that I've otherwise been talking about in the tutorial. And the results, again, let me not go too much into detail, but it goes sort of, this is a compliance design. This is the buckling without global buckling. This is global buckling and local buckling. And the last one is global buckling, local buckling, and plasticity or yield stress constraints. And we see we get this well-known rounding here. And again, it's interesting. The interesting thing is, does it work when we dehomogenize? And in fact, it does. So with all these four structures have the same volume fraction, but the last one actually has a factor of 7 higher buckling value, both locally and globally, compared to the compliance-based design. And we, well, almost satisfied the yield stress constraint. So I think this shows that you can really do advanced things with multiscale topology optimization and with the knowledge of both density approaches and multiscale and microstructures and all this stuff. So just the last thing here is you have to be aware of when you introduce yield stress constraints also, it becomes material dependent. So in this case of the buckling and yield stress, you get different structures if you have steel or you have TPU. Steel is entirely governed by plastic yield stress constraints, whereas TPU is entirely governed by the buckling constraint. So that's another sort of interesting point when you are doing multiscale here. So this brings me to the end. I hope I have inspired people and shown all the fantastic things you can do here. I think there are still multiple open problems. One thing is we get these extremely advanced structures with mapping and grading and all this stuff. And right now we are mapping them to fixed grids, which is really a waste. We are working with my PhD student Markus Holm on doing some better parametrizations that should make it much easier to dehomogenize. And I think there's a lot of potential in those directions. This stuff with mapping of advanced microstructures is totally untapped. I'm only showing a picture here. We have not done any research on that. And then all these interesting things, still nonlinear structures. I believe nobody has done dehomogenization with nonlinear structures or materials yet. Multiphysics, the more interesting it becomes, the more interesting maybe the microstructures are. And we still have some issues with the post-processing and verification. And I also have a personal dream of at some point do the gigascale wing design, but with a multiscale approach where we take both multi-loads, global and local buckling, and stress and manufacturing constraints into account. So I think still open, interesting things to do there. And so that brings me to the conclusions and recommendations. Well, I've advocated dehomogenization here. Very importantly, we have to use isotropic microstructure for the right reasons. And that reason is not stiffness alone. It has to be optimal, or it's only optimal if you have other criteria. I warmly recommend to compare with baselines. So the rank 2 homogenization code provides you with a lower bound on the stiffness. Use it when you introduce other methods. Interestingly, separation of scales doesn't seem to be a big problem when we do dehomogenization because it's based on optimal structures that have tension compression behavior, no bending behavior. And maybe, well, not to go through all of them, I think, and that's sort of my main message here, I'm giving it 3 tutorials on the density approach. Grégoire will give 3 tutorials on the level set approach. In my eyes, they're not that different. Really, everything is overlapping. Things are very similar. And I think in the field, we should try not to sort of differ so much between what approach we are doing, but rather the quality of the results and the efficiency of the algorithms. Because they are similar, and this is our goal, not whether we are using level set, density, topological derivative, or whatever, because they are really very much similar. So that was the last word. I've collected again some very ego-centered references here. Obviously, there are other people working in this field, but I think these are the ones that should be interesting for what I've been talking about today. So thank you very much for your attention.
Thank you very much, Ole, for this interesting deep dive and overview of this stuff. So just because I forgot to say it before we started, if you have any questions, please at the bottom of your screen, you have this Q&A button. It's like a speech bubble with a question mark. Enter your questions in there. There are a few already, but if you have any, please enter them in there. Okay, so let's take the first one. So you kind of already touched upon it a little bit throughout, but so this person is asking about nonlinear problems. So both Navier-Stokes, but I think you mentioned a little bit about that. But let's maybe expand it to what are some of the difficulties or opportunities when having nonlinear physics?
Yeah. So I already touched a little bit on it. So obviously the nonlinearities, now you get microstructures that are somehow depending on the deformation history or the strain history and all these things there. So it actually becomes harder to find the optimal microstructures, right? So if we have linear elasticity, we know it depends on the principal stress directions and the magnitudes, and then it's given. And then we can pre-compute either by a database or by the analytical rank materials. Whereas for nonlinear materials, you sort of get that the optimal microstructure at a certain point would depend on the deformation history. And so then would you start actually optimizing this microstructures for different loading histories and then save those in a giant database? I think that's an interesting question. And maybe again here, that could be something where you would use AI to look at optimized microstructures from many different load histories. And so that's where I see, again, an advantage, a potential advantage of AI. The other thing you could do was to just say, okay, we don't care about whether we are using the optimal microstructure, but just a microstructure that probably will do the job. That would make it much simpler, and in that case, it's more just the nonlinear analysis and the microstructure dependence on the size of the deformation. So I think it's really an interesting area to go into. I could also, it's a long answer, but people have sometimes said, well, it's good that you did it for stiffness optimization, but what if we don't know the optimal microstructure? And well, in that case, one possibility, and I think I said it also, could be to run with this local volume constraint, because that sort of enforces a local microstructure, and then you can learn from what is the optimizer doing with the local microstructure, and then maybe afterwards parameterize that and use in a more efficient homogenization-based approach. So long answer, but I hope it's satisfactory.
Very good. So then we have someone asking if there is any work on applying this to dynamic loading or non-concurrent loads.
To dynamic loading, no, that's no, probably not. And that would definitely also be an interesting thing. So again, there, you would have more in your database, and you would also have the mass, which to include, but probably not. The interesting thing is, of course, if you're still assuming that your wavelength in your vibrations is much larger than the microstructure, then it should be fairly straightforward. It's just also adding the mass in your interpolation function. But the case where you start having the wavelength comparable to the microstructure, then you're sort of getting to the metamaterial business. And then you would be a little bit like the buckling load. You cannot just do homogenized properties. You have to do Floki-Block wave stuff and all kinds of stuff, and it gets really dirty. But even there, I think it should be very interesting. Now that I'm talking, actually, something very close to the de-homogenization by Pans and Trabelsi was done by what were they called, Rump and somebody in photonics. So there they looked at optical wave propagation in periodic structures that were modeled with this, you could call it a kind of de-homogenization, but they didn't optimize. So there has been some works in de-homogenization, but not regarding optimal structures, I think, for dynamics.
Okay, yeah, thank you. So someone is asking for your thoughts on buckling microstructures, especially given their sensitivity to defects and perturbations. Is it possible to sort of account for those when designing these multi-scale structures?
Yeah, an excellent question. So actually, we have papers, I didn't list them here, but together with Lucas Blum also, where we tested experimentally these hierarchical microstructures. And the people before that said, when we did these hierarchical microstructures that you sort of see in the upper right corner here, they said, well, it's good you're maximizing them and getting multiple simultaneous failure modes. And so these are going to be catastrophically buckling. But again, our experience was that the buckling load in physical experiments was actually higher than the linear buckling analysis. And so that sort of already accounts for it. And also this sort of, you could say, redundant structures also made it less susceptible to failure, because it could break a little part of it and then there would still be other parts there. But that being said, that is actually my main interest these days, is to look at optimization with randomness and make things robust with respect to either manufacturing errors or randomness of perturbations. And Federico, who is doing the buckling stuff, is actually also developing methods for that. So I think that's definitely an interesting area. But sometimes we get this robustness for free when we also optimize. And you could say that this buckling optimization of the microstructure is a multi-load case, because we are optimizing for any imaginable wavelength. And in that way, we sort of make it robust to any variation.
Yeah, thank you. Not so many questions this time. We have a few that are not strictly... Okay, I'm going to take this one that just came in because that's more relevant. We have a few that are not fully in line with today. So how would you incorporate manufacturing constraints? Say the structure is 3D printed and the structures must come from the toolpath of a robotic arm.
Yes, very good question. So I would, you could, well, again, you could select microstructures that are printable. So you could say that you cannot accept a microstructure that has this overhang. And so then your database of microstructure possibilities, you limited that to locally manufacturable structures. And then interestingly, again, right, very rapidly, then you don't have an optimal microstructure. And then probably it turns out to be better to not use microstructure at all. So I think that's very important, right? We are doing so many, it looks so fantastically beautiful, but they are sort of sensitive, that they are not optimal if we mistreat them too much. And so if we ask for too much manufacturing robustness, then maybe microstructure is not optimal again. And then you would then maybe go back and say, okay, so now we don't just optimize for buckling or other things, we actually optimize for this load path redundancy. And we have sort of been making these claims like also for the local volume constraint. And here that, and I made this claim just before also, that by having these hierarchical structures, you get redundancy and therefore maybe better. But I think to really make sure that this claim holds, you should actually optimize the structure for the optimal redundancy and then conclude from that. But in my eyes, this optimality of microstructure is a very fragile thing. And if you perturb it too much, then the optimizer just says, I don't want microstructure, guys. We saw it also in the, I think in the last example here, right? Here, even for steel, it doesn't want microstructure because it will yield before it has any advantage of the microstructure, right? So all the time, we have to be careful. We can make some claims and say, hey, we improve buckling by introducing microstructure, but then we actually have to try to optimize it using that and not just claim that we hope that this microstructure will make it better or more redundant or stuff like that. So verify our claims is also a recommendation for the field.
Okay, I'm gonna allow myself to insert a question from myself here. So, have you ever tried using the de-homogenized result as an initial guess for a full scale? And
Oh,
if
yes.
so, does it actually, like, do you see any significant improvement, or does it not do any huge changes?
Well, we have that's a good question. Yeah. So we have done it in different ways. We had one project and a paper also where we actually did the de-homogenization and then extracted a truss structure from that, and then optimized with node-based shape optimization. We optimized the truss structure afterwards, and in that way got a fairly efficient approach to it. Also, if you took one of these de-homogenized designs as starting guess, that gives you a fantastic starting guess. But then the problem is that we de-homogenize it to an extremely fine grid, right? So it becomes very expensive also to run it there. So you're sort of losing the great benefits. So in my eyes, if I de-homogenize and do one post-analysis and I'm within, say, 5% of the homogenized predicted result, I'm thinking maybe it's not worthwhile actually also post-optimizing.
Yeah. Just one question. I'm assuming you have time for more questions, but
Yeah.
how do you see the trade-off between computational tractability and physical accuracy when moving beyond periodic homogenization towards more realistic microstructures?
Towards more realistic microstructures. Yeah, so I guess I showed these structures in the previous one where I showed this randomness on the surfaces. Yeah, so ideally you don't want really to model every manufacturing defects, right? You'd rather say, hey, let me design a structure that I know will be insensitive to all these manufacturing defects. And so in that way, you would not need to do such an expensive model. So that's sort of my goal these days, to find efficient methods to avoid making too heavy computations to include all manufacturing variations, right? But it's a difficult one, right? And especially some 3D printing stuff, when you take a microscope and look at your microstructure, you want to run away screaming, right? They are really far from the ideal situation. But then you could also ask, if they are that shaky on the boundaries, does any airplane pilot want to fly with a 3D printed part like that? So I think probably the physically realistic uncertainties will be less for practical problems where people want to use them for practical means. And so again, I think it's often like topology optimization adapts to manufacturing, but manufacturing also adapts and becomes better. And so somehow we meet in the center, and possibly some of the activities we did in the beginning, like also all the overhang constraint stuff, right? There we have spent a lot of time on that in topology optimization because the 3D printers could not have overhangs. But then I think with time, they're getting better and better to avoid having problems with overhangs. And then we don't need to take that into account in optimization. So it's this, I've earlier used an analogy that AI and TO constitute the perfect marriage, but in all marriages, the partners need to adapt to each other. And here the question is, how much does topology optimization adapt to AI? To AM, or oppositely, how much does AM adapt to what topology optimization shows is theoretically possible? Those were some philosophical thoughts.
Yeah, and so let's do this one. So you mentioned the AI by mistake now. So some people have asked about your opinion on that, and I think we can. One suggest you go back and watch the first lecture on YouTube. There are some comments on that. But someone is asking specifically for your opinion on these pins, so physics-informed neural networks. Do you see any potential for them to replace anything?
That's a tough question. I actually have a slide I have used sometimes where people in fluids, it's a Nature Computations paper that was published 1 or 2 years ago, where they were reviewing various AI-based fluid solvers. And they were sort of concluding that pins were not amongst the most promising parts, so they actually didn't review them at all. And then they went on to say that there were a lot of sort of comparisons to weak baselines. So people were, when they were claiming that AI was doing better solutions than established fluid solvers, then they were comparing to crude convergence criteria and bad solvers and stuff like that. So honestly, I'm not against AI. I think it has potential in many places. I actually, in this talk, I said, well, for interpolating material properties for our database to be used by the optimizer makes sense. The de-homogenisation stuff did turn out not to be as efficient as the Phasor approach, but still there, I see potential in different subtopics for use of AI, but still using AI directly to optimize, I don't think it's the right way to go because it's interpolating, not extremizing. So, yeah.
Okay, and I'm gonna call this the last question for today. So you've made it clear that the performance advantage of microstructures can be fragile compared to sort of standard methods for stiffness problems. Do you know if the margin of improvement and the opportunities for performance advantages is different for thermal problems where maximizing surface area can be a key factor in the design?
Haha, yeah, good question. Yeah, so I guess I actually should give it back to you, Joe, because you did the de-homogenization of thermal problems and used surfaces. Yeah, so that's a really interesting question here. So obviously there, if you want to maximize the surface area, that's a little bit like having the local volume constraint, right? Saying, because there you also indirectly maximize the local surface area. So in that sense there, it should be more robust. There, if you don't have the microstructure, then you don't have surface, and therefore it will be a bad structure. Yeah. So I think I'm answering and saying yes. For that case, it should be much more robust. Good point. There is this interesting thing in when we talk about fluids is that for elasticity, the effective properties don't change with regards to the periodicity I impose, but in fluids, the permeability depends strongly on the length scale. So in that sense, in fluids, you should in principle include the realization periodicity in your optimization because the structure is changing. And I think you did some studies on that in your papers, right, Joe?
Yeah, yeah.
Yeah.
Yeah,
Yeah.
Yeah, I just want to make one cheeky comment also that the maximizing surface area is not always necessary for thermal problems, even though that's what we often learn. And I
Yeah,
won't
I
go
guess
into
if you
details.
maximize it too much, there's no conduction
Yeah,
left, right?
yeah,
So
convection.
then
Yeah,
it's actually a nice problem that you don't need to have a volume constraint. It should find the best volume itself, right?
yeah, yeah.
Yeah.
Okay, and apologies to the last few questions. They're sort of deviating in other directions, and I think we've already gone a bit over time here. So let's thank Ole for his presentation today and all three of the lectures. As you hopefully know, they will all be on YouTube. The two first ones are already there with timestamps in the comments. I will try to get the timestamps done for the new one relatively soon, but otherwise you can watch the whole thing again if you need to. I just want to say again that we will have 3 lectures on the let me just open that, on the level set method, as Ole also mentioned, so we'll get some different perspectives there. So that will be in May, and the sign up information will come out different places soon on our website, the mailing list, and my LinkedIn. And regarding the website, we might be moving it, we might not be moving it. We've had some issues. The mailing list, we're also going to change to a new system. I'm hoping I can move the original list that we have, but everything should become a little bit more automized, hopefully. And then maybe we will also have a more standard webinar in April, not a lecture, but one of the more old school versions we used to have. But nonetheless, you can keep up to date on the various channels. And again, thank you, Ole, and thank you everyone for joining.
Thank you, Joe. It has been a great pleasure, and thanks to all the people listening.